Today's PowerPoint/video is on redox reactions in acidic solutions. This entire chapter of electrochemistry takes a closer look at redox reactions. Before, we were just looking at redox reactions just as is. We were ignoring the kinds of state that they were in. But frequently, redox reactions are solution chemistry, and they can be in an acidic condition or a basic condition, and whichever condition they are in changes how the chemistry is going to function. So to quickly recap our redox reactions, we know a redox reaction is one where electrons are transferred. We know that reduction is when we are gaining electrons, and oxidation is when we are losing electrons. You can sometimes remember this from the term oil and then rig. Oxidation is losing, reduction is gaining. Much like balancing equations for matter, we had to learn how to balance equations for electrons. So we know what a general redox reaction is. But redox reactions don't typically occur in solid, liquid, or gas form. In fact, they frequently occur in solutions. The reason for this is because ions are typically found in an aqueous solution, not necessarily their solid, liquid, or gaseous state. So that means we can't just think about these abstractly. We have to think about these with solvents and solutes and the properties of solutions. So think about this. A solution is a homogeneous mixture. That means the ions are spread out throughout the solution. There's not a chunk of ions at the bottom of a beaker for either whichever one's reducting or which one's oxidizing. They're spread throughout the solution. When an ion is dissolved, the water molecules surround the ions. Remember, this is because we're dealing with water here, and water is, of course, a polar molecule. So when an atom has to gain or lose an electron, the solvent, and in this case, water, is going to have to interact with the electron. Let's take a look at the next slide to see how that happens. All right, let's take a look at how redox reactions have to interact with water molecules when an ion is in solution. Let's consider for a moment that we've got an atom of copper 2+. Copper 2+ has lost 2 electrons, so it has a positive charge. We're going to assume this copper 2 is undergoing reduction. So that means it's going to have to gain an electron. I've drawn in a little electron in blue down here just for reference when we talk about this in a little bit. If the copper 2 atom is in a solution, it means it had to have been hydrolyzed. And that's where we get that wonderful vocab word, hydrolyzed. It means the water molecules have surrounded the copper ion. Now, why does this happen? Well, it happens because water is a polar molecule. We have a negative side of the water molecule because it has a lot of valence electrons. And on the other end, we have a positive charge because those don't have any valence electrons around it. So now when the copper 2 ion is in solution, the negative sides of the water molecules will be attracted to that positive ion, hydrolyzing and surrounding the copper 2 ion. It doesn't just happen on an X and Y coordinate, it would happen above and below that copper 2 ion. Now, Mr. Killian, why do we care, you might ask? Well, it means that the water molecules have completely surrounded the ion. Therefore, if that electron's going to interact with the copper 2 atom, it has to go through those water molecules. This isn't some sort of running back that can break through a couple tackles and go into the second. This is an electron. That will not happen. It will not just go between the water molecules. That means it's going to change the chemistry that's going on if it has to interact with the water molecules first. So why do we care? This means that the solvent is actually part of the reaction. Before, we could just say something was aqueous. But now, in redox reactions, and in only redox reactions, the solvent is part of the reaction. The water molecule is somehow able to prevent electrons from interacting with the molecules inside. We wouldn't have any oxidation or reduction. So therefore, we need to modify how we are balancing redox reactions. And I want to emphasize this. I gave it its own little thing. We're not changing. We are modifying. We are simply adding on a little end to incorporate the fact that the water molecule matters and the solution chemistry matters. I really would have to hate to read through all of these rules, considering there's 6 of them. But let me just explain a couple of big points. Remember, we are modifying the rules that we had before. We're just adding some stuff to the end. In fact, the stuff that we're adding to the end are steps 3 through 5. The steps All the other steps are ones that we would have done before. First, you're going to separate your equations into half reactions, your reduction half reaction and your oxidation. Then you're going to balance for mass in your oxidation and your reduction. Steps 3, 4, 5, and then eventually 6, we're going to balance for oxygen by adding H2O. This is because the H2O is technically part of our redox reactions when we are in an acidic solution. Likewise, we have to balance for hydrogen by adding H plus ions because, again, we're in an acidic condition. Then we're going to balance the charges with electrons, and then we're going to combine those equations and eliminate any like products or reactants. Let me give you an example and walk through it. Let's say we've got this following redox reaction. Permanganate ion reacts with iron 2 ions to create iron 3 ions and manganese 2 plus. We can see that there are two parts of this reaction. There's the reduction and there's the oxidation. The reduction is the manganese. It is going from a +7 state. How do we know that it's a +7 state? Well, that's because oxygen is always -2. If it's always -2 and there's 4 of them, it has an overall charge of -8, which means that the manganese has to be a +7, yes, something out of a +7 oxidation state in order to balance out that charge. Manganese on the other side is just a simple monatomic ion, which means it's a +2. We went from a +7 to a +2, which means we gained 5 electrons. And so that's how we know that it is reduction. On the other side, we have iron going from 2 plus to 3 plus. This is a little easier. We're obviously going from a less positive to a more positive, so that means we had to have lost some electrons. So that is why it is oxidation. So far, this is the same exact thing that we would have done before. We're going to separate into our half reactions. Let's start off with the one that's undergoing reduction first. The first thing we're going to do is follow that first step. Balance for mass. Well, it's already balanced for mass. Manganese on one side, 1 manganese on the other. Now we're going to balance for mass with oxygen. There are 4 oxygens on the reactant side, so we need 4 oxygens on the product side. So we're going to put 4 waters down because 4 times the 1 oxygen gives us 4 oxygens. Don't worry about the hydrogens. We'll deal with them in the very next step. Now we see we have 8 hydrogens on one side of the equation, so we need 8 hydrogens on the other side of the equation. And so we just simply put 8 hydrogen ions. Where do these hydrogen ions come from? We are in an acidic condition. So that means we can add these H plus ions when necessary. Now that that's done, we're going to balance for charge. We see that we're undergoing reduction. We're gaining 5 electrons, so we're going to put 5 electrons as one of the products. Remember that little trick? Reduction means reactant. Your electrons are a reactant. So now this is our final half reaction for reduction. We're going to combine this with the final half reaction for oxidation, which we'll solve for right now. This is the half reaction for oxidation. It's very simple. Iron 2 plus going into iron 3 plus. You'll note it's already balanced for mass, and there's no oxygen and no hydrogen that'll interfere. So all we're going to do is add that electron just like we normally would. We're going to, though, multiply by a factor of 5. And the reason why we're doing this is because we have 1 electron, and we know from our other reaction we have 5 electrons. So we need to still multiply by a factor to balance out all of the electrons. But now we're actually done. This is the final half reaction for oxidation. So now we're going to take that half reaction from reduction, add it to the half reaction for oxidation, and get our final reaction on the second slide. Here's our final reaction. We've combined the reduction, which is in yellow, with the oxidation, which is in green. We note that there are 5 electrons on both sides of the equation, which means we can cancel them out and get our final redox reaction. 8 hydrogen ions plus permanganate ion plus 5 iron 2 ions will create a manganese 2 plus ion, 4 water molecules, and 5 iron 3 plus ions. Why is hydrogen and why is water in this reaction? It's because we're in an acidic solution, which means water is a solvent and it needs to react in order to be able to transfer those electrons, and the H plus ions come from the acidic condition. Hopefully you found this PowerPoint presentation a little helpful. I have a worksheet for you guys to try some on your own. Be sure to go back to that slide with all of the rules should you need any help, and if you need any more help, feel free to email me. Have a great evening. I'll see you guys tomorrow.